There we go. Okay, so thanks for the introduction, Gail. Hi to everyone. So I will speak about adding new features to Nilearn. And yes, I will do so on the example, as Gail mentioned, that I've been part of myself, which was bringing support for cortical surfaces to Nilearn. So I want to go through this example a little bit, but then also based on it, outline a few lessons or ground rules that I've learned in the process. And then more generally speak a little bit to the question if and when adding new features is a great idea, or if it might be a case of feature creep. And finally, say a few words about the future of Nilearn, the future of cortical surfaces in Nilearn. So to start off, just a little bit of context where I was at when I started contributing to Nilearn. And I just pulled this off my internet history. I started programming in Python in 2013. And before that, I had learned a little bit of MATLAB, but really nothing to write home about. And I joined GitHub in January 2014 to make my first small pull request to NiPipe, which got merged. And I was very lucky at the time to work as a student with Chris Gogolewski, who was one of the core developers of NiPipe and really got me into the world of open source software. But after that, so I made some more contributions to NiPipe and like first issue to another software, but mostly I used GitHub to maintain the little tool I was working on for my master thesis. Then in summer 2015, through a colleague, I got to be part of the Nilearn coding sprint. And this was really kind of a game changer for me in terms of my ability, and I think especially my confidence in the ability to contribute in a meaningful way to scientific software. And then since then, what has kept me moving forward in that direction, I would say, are really brain hacks in a big way, coding sprints, and also the Google Summer of Code that I did as a student and as a mentor as well. So, but at this first coding sprint that I went to, I was a bit at a loss of what to do. And I guess Gail tells the story a little bit differently. But so I chatted with Gail about what could be useful for them and what could help me learn. And at the time, I had started my PhD and I worked a lot with cortical surfaces. So most of the people in the Nilearn development team did not work with cortical surfaces, but I could apparently convince them that it would be great to support them in Nilearn. And so Gael suggested why I don't give a shot of integrating cortical surfaces in Nilearn. And I was a bit intimidated, but also intrigued and probably sufficiently naive to go for that challenge. So again, this is less than 2 years after I wrote my first lines of code in Python. And the reason why I want to emphasize this is really to encourage people that maybe feel like they're not in the position to make meaningful contribution to the software, because my experience has really been that this is really one of the things that you only learn by doing it. Yeah, so the plan was to bring cortical surface into Nilearn. And since I'm not sure if how familiar everyone is with cortical surfaces, I wanted to give like a very brief overview. We know that the human cerebral cortex is essentially a thin and highly convoluted, highly folded sheet of gray matter. And MRI produces volumetric images. At the same time, it is essential for a number of questions and applications to represent the cortical sheet as a surface instead of a volume. And the most obvious example is visualization. So surface representations allow us to see much more of the cortical sheet at once than if you just cut through a volume. And they can also be inflated. They can also be inflated to expose the areas that are buried in the sulcal depth. Then another case is the analysis of spatial relationships or cortical topography along the cortical sheet. And the idea here really being that while, for example, here across the sulcus, these areas seem quite close to each other, but the biological relevant distance is really following the cortical sheet, because these areas don't interact with each other in the way we think about across the sulcus. So, and this becomes really important also for smoothing along the surface, etc. And then lastly, now that we have increasingly sub-millimeter resolution, especially with 7 Tesla data, the data can be resolved at different depth of the cortex to capture variation across layers. And for this, again, we need a coordinate system that follows the cortical sheet rather than arbitrarily cutting through it and cutting it up into cubes. So cortical surfaces are typically represented as triangular meshes. And a triangular mesh consists of 2 components. First, there's a set of endpoints defined by XYZ coordinates, and then a second set of face indices that determine which 3 points should be connected to a triangle when drawing the mesh. So these are indices into the sets of points. And in addition, there can be data, this is often called texture, associated with the mesh. This is an n-by-1 array that associates a value with each point of the mesh, or it can also be a vector, for example, a time series that is associated with each point. And you can see already that this is very different in terms of the kind of data and the format of the data that we're working with from our classic nifty image, which basically would come as a single 3-dimensional or 4-dimensional array of values, and maybe some associated metadata. So what this has led to in terms of neuroimaging software is that most software packages, and to an extent scientists, focus either on volumes or on surfaces. And certainly the most popular software for creating and analyzing cortical surfaces is FreeSurfer. So FreeSurfer is a great resource. And if the analysis you want to do is implemented in FreeSurfer, you are probably fine to just stay inside the FreeSurfer universe. However, if you want to do a different analysis, something more advanced, or really just tweak the analysis in a way that they maybe hadn't foreseen, it can become quite tricky. So the idea is to enable Nilearn to work with cortical surface data. And again, as Gael said, the idea is not to provide functions to like extract these surfaces or align surfaces to do all of this pre-processing, but really to do statistical analysis on surface data. Still, this is actually quite a big extension, and the question was, where do we start? We started with plotting, and this might seem, or to me at the point, it seemed a little unintuitive, because why would you implement plotting surface data before you really have any way to analyze surface data? And part of the answer is that, as I said, visualization is an important application in and of itself of cortical surfaces. But beyond that, it was, I would say, quite a neat move, so to say, because implementing the plotting functionality solved, or made it necessary to also solve 3 issues that would then pave the way to an extent for any surface-based function that might be implemented at a later stage. So first, it had to provide the ability to load surface data from file. Then it required some internal representation of surface data, and it also enabled, like once implemented, the plotting would also enable everyone to look at surface data at every step along the way at a point where we might want to implement more complex processing in the future. So you can read up on some of the details in this report, but just here in short, we implemented loading using Nibabel, I don't know how to pronounce it, which is also used for the loading of volumetric data in Nilearn already. And similar to the volumetric data, the loading functions take either a file name or a surface object as an input. And supported formats are currently GIFTY or any of the FreeSurfer type formats. And there are 2 separate functions, one for loading surface meshes and one for loading surface texture. Then internally, a surface object is represented as follows. So a mesh is a list of 2 NumPy arrays, one for the coordinates of the points and one for the indices of the faces. And a data or texture is represented as a simple NumPy array. And I will talk a little bit more about the potential future of this and maybe the issues with this later on. And then, so the bulk of the work was in the plotting, of course. We implemented this using matplotlib's plot trisurf function. So this is a function that plots triangular meshes. However, we needed to embed this function in quite a bit of extra code that handles, for example, the interpolation of point data to the values on the faces, but then also things like masking and thresholding, the default orientations of the brain, etc. And we did this in a base function called plotsurf, but then also provided two additional functions with preset defaults for plotting of regions of interest or parcellations, as well as statistical maps. And with this, we kind of follow quite closely the structure that already existed for plotting volumetric images. And then we also made two usage examples for these functions. The first is just a plotting of the Destrieux atlas on a convoluted and on an inflated surface of the FS average 5 space. And then there's this a little bit more complex example that uses a mask of the posterior parietal cortex as a seed, and then runs a seed-based functional connectivity analysis on a public resting state fMRI data set projected on the surface. So this results in a group level correlation map that is computed and then plotted to showcase these different plotting options. And this is more or less where I had left off, because I had to finish my PhD and move to Portugal. But then, of course, one of the most rewarding things in contributing to a larger project is that ideally your code keeps being built on by others. And so some of the things that had happened or that has happened since is that Nilearn now has the ability to project data that is given in volumetric space onto a surface mesh using these different types of interpolations. So that means that even if you do the analysis in the volume, you might be able to visualize your data on the surface. And then there's also this interactive HTML viewer version of the surface plotting where you can switch between, for example, between the hemispheres or inflated or piled surface, and move around. So this is really cool. And I think most of this was contributed by Jerome. So for me, going through this example of adding surfaces to Nilearn, I thought about what, for me, were the big takeaways from this experience. And I came up with three that I think might be helpful for people who want to contribute in the future to Nilearn, but also beyond Nilearn, I have found these really instructive for my own projects as well. So first is avoid additional dependencies. So these are the existing dependencies of Nilearn, if I'm not mistaken. And let's say you will meet a big resistance if you try and add a feature which makes Nilearn dependent on a new library or package. And, you know, this is on the one hand, it's in the interest of keeping Nilearn easy to install and to handle for the user. And on the other hand, of course, from the development side, the more external libraries we use, the more susceptible the software is to changes in those libraries or bugs, or just simply keeping track of all of these different versions of different libraries, test against them, etc. So in the case of surface plotting, there are fancier libraries for plotting surfaces, for example, Mayavi, but this is really a bit heavy and it's a bit hard to install. And so hence was the decision to just use matplotlib, which was already a dependency for plotting volumes in Nilearn. And this has a lot of advantages in terms of making it comparable to the volumetric plotting. It also has a few drawbacks, especially since this function in particular can be a bit slow for high resolution surfaces. And again, here, what I think was quite eye-opening to me was that when we ran into this issue, the approach of other people in the Nilearn team was to try and push for the function to be improved in Matplotlib. So of course, this is a much more sustainable approach, and also that kind of benefits the community at large much more than if we try to kind of work around and reinvent the wheel inside Nilearn. Yeah, so then the second lesson, I think for me, was to write tests for each part of my code along with the code. And I'm not sure if I'm preaching to the choir with this audience, but I think I just want to emphasize this also to myself again, because I think I tend to, like, you know, at some point forget how great of a habit it really is to write tests for every little function, even if it's just for myself. Because once you kind of are in the habit and are familiar with the basics of testing, coming up with a test is often quite quick because you're already thinking about, you know, what is this function supposed to do, what is not supposed to do, and it actually helps you to think about it in a really formalized way. And of course, it will make it much less likely that you accidentally break your function or introduce a bug later on as you're developing and extending it. And for sure, if you want to add something new to Nilearn, you will be asked to add tests at some point for your new functions as well. And then third, and I think this is really something quite special about Nilearn, and I think this is something that Bertrand might speak about later as well, is that in addition to this unit tests, new features are typically required to come with an example. And an example means that, first of all, you provide a data set that can be downloaded, like a public data set that can be downloaded through a data fetcher. So this can be already downloadable somewhere, like this can already exist on the internet, or you can also make it available or host it through Nitric, through the Nilearn Nitric account, I guess. And then you'll have to write a data fetcher and test the data fetcher so that the data can be downloaded easily through the software, and then write the example. And there are some rules, so it should be clear and instructive, but then there are also like some just formal rules so that it gets rendered nicely in this example gallery. But honestly, like when you have the blueprints of the others, it's quite straightforward, I found. And I really think that this is one of the aspects that sets Nilearn apart, that for every function, there's an example with good explanation and with the code and the data you need. And this makes it easy to get started and also can make it much easier to troubleshoot. And this is something that we adapted in one of my own projects completely like this, because I think it's a really cool aspect of Nilearn. But yeah, just to say, like, once you add a function, there's actually going to be a lot of other things that you'll need to add. At the same time, doesn't mean, of course, that you yourself have to edit. This can also be a collaborative process. Yeah, and I think also, finally, the developing with an example also helps to keep the focus on the target in a way, because maybe one of the most important questions to ask when adding a new feature is, should this feature actually be added? Because there's this concept of feature creep or scope creep, or however you want to call it, which basically states that if you keep adding new features, even if the features individually are quite beneficial and good, at some point, there will be a point where you end up with a software that is confusing and hard to use. And because it just becomes harder and harder for the user to find the features, to understand the features, to understand the main functionality and flow of the software. And it also becomes harder to maintain the software, of course. And so in a way, there comes a point as you add more features where there's a trade-off between quality and quantity. And of course, then the trick is to find that point. But I just think in general, it's really important to keep this in mind in the open source software community and for scientists in particular, because so this comic might not apply because we don't usually have a boss that's like tells us to, implement this feature if you like it or not. But instead, I think we might have a lot of individual users and contributors that are interested in a particular feature for their scientific question. And on the one hand, that's great because that gives motivation to contribute, right? If this is something you want to use yourself. But at the same time, I think it is important to still keep an eye on like how many people do actually want this, and what does this actually mean in terms of maintenance. And so that there are situations where actually not adding a feature might be the right choice. So it's just something to keep in mind when contributing and also when reviewing other people's contributions. And something I have found for myself kind of a bit mind-boggling, but also kind of interesting, is how this trade-off between complexity and novelty, like adding new features, really depends on the goal of your software, or at least that's where I have fallen at this point. Because for me personally, just as an example, how I think about this for Nilearn on the one hand, and then Niras on the other. So Niras is a package that I made together with one of my PhD supervisors, with Pilou, and this implements algorithms that are specifically designed to handle high resolution 70 or beyond data, and kind of support the new sequences, support the new analysis that come with this data. And I think in a way it's been a little bit tricky for me in like working on this project, coming with a lot of the principles I guess I got from Nilearn, and of course not being able in the same way, because it's a very different scope and very different project, to implement them in the same way. So I think what I've learned is that, like even the mission statement of these two packages. So Nilearn in its mission statement says it's supposed to be approachable. So the ease of use is really a strong goal here, that people are relatively, like that it's easy for people to start using these. And whereas for Niras, the intention was really to improve on the issues that were there with installation usability of its predecessor CBS tools. So in other words, it's already a good result for now for us with Niras, to make these tools more approachable than before. Then Nilearn targets a large number of quite diverse users, while Niras at this point is mostly used by people that are already fairly expert in this subfield that is targeted in this like high resolution neuroimaging or MRI. So in other words, if I tell a Niras user that they have to find a way to convert their file format or to like load that data in a NumPy area before using it in Niras, and like make sure that they do this right on their own, they will probably be like, okay, I'm sure I can like figure it out, because that's a price they are willing to pay to use these algorithms. Whereas a Nilearn user, I think rightly so, to an extent, would expect that this is handled in a standardized and robust and kind of tried and tested way internally. And on the other hand, I think while it is quite acceptable to expect a Nilearn user to have their data quite in a somewhat standard contrast, maybe have it even registered to a standard space, the typical Niras user will come with kind of a wild mix of the latest experimental contrasts and their super high resolution study specific template, and then not expect that it's plug and play, but expect that they can adapt their algorithms to handle their data. And then lastly, Nilearn aims to offer versatile analysis that have been shown to really work robustly for a set of different applications, whereas Niras provides like these really highly specialized algorithms. Sometimes they've just very recently been introduced in this still quite volatile subfield of of neuroimaging. So what I'm trying to get across is that the considerations around adding a new feature are hugely different, at least for me, for these two different projects. So while Nilearn, it's much more important to keep a check on complexity, to make sure that the new features are robust and are easy to use and make sense in the larger frame of Nilearn. I think for NIRES, of course, these considerations are important, but then there's also a much higher value in making very new algorithms available for people to try them out, to develop them further, to compare them to their own, etc. So kind of like different projects have different missions and therefore different requirements, and just, I think, a good exercise to make them explicit for yourself. Yeah, so keeping all of these lessons and considerations about adding new features in mind, I want to end by returning to the topic of cortical surfaces and their future in Nilearn. There was a question earlier about this already, and there has really been a substantial discussion on GitHub. It's quite interesting that you can read up. And so in general, I would say that there's an agreement that extending support for surface data is a good idea, but there's not an obvious way how best to do this in keeping with Nilearn's principles. And the idea is that the next logical step would be to create a surface masker analogous to a Nifty masker. And you're probably familiar with the Nifty masker, which can take a file name or a Nifty image object as an input and then perform some spatial operations if you want, like masking, resampling, smoothing, and then some signal processing operations of the time series data. And for a surface masker, I would say, this is the way I see it, is that the time series processing would pretty much do the same. All of the spatial processing, if it's supposed to be supported, it would need to be re-implemented because it's just fundamentally different for surfaces than for volumes. But this, I think it's not even the big problem. I think the big problem is really in this seemingly trivial step of input, of loading and representing the data. And so I mentioned before that the current implementation is we support FreeSurfer type file formats and GIFTY as inputs, and we handle meshes as and textures separately as NumPy arrays. So the problem with that is that while that seemed as kind of the right thing to start with at the time, there is really no consensus at all in the community for representation and file formats of surface data. So sure, most people probably use the data formats produced by FreeSurfer, but even those are really kind of confusing and idiosyncratic, I would say, unless you really, stay within the FreeSurfer universe. So you have all of these like pile, sphere, anode, thickness, and you need to handle them in different ways. They represent different kinds of data. Then there's GIFTY, which is an attempt to have a standardized data format analogous to Nifty, but it's by far less widespread than Nifty. And then there's also SIFTY, which is used in the Human Connectome project. And then there are other formats that are not even really they are not specific to neuroimaging data, but just to meshes in general, such as VTK, PLY, OBJ, etc. So, like, what do we do with this? And then to make it worse, it's not even about deciding which formats to support and then make loading functions for this. That would be one thing. But then the problem is that even the way that data is handled in these formats is different. So some of them keep meshes and textures together, and in a way that is good because it makes it easier to keep track of the texture that is associated with the mesh, etc. At the same time, many people actually prefer, and some of these formats only allow, to store meshes and textures separately on disk, because you can have different textures for one mesh, or you can have different meshes for one texture, and you don't necessarily want to store many replicas of the same information in different files. And then also, typically, the hemispheres are handled separately, so you also, in a way, need to keep track of the two different hemispheres of the same brain and linking those two. So all of this is a bit of a headache. But I think that also there's been some really good discussion, and there seems to be a tendency to move towards using Neubauer's Gifty image object, at least internally. But hopefully during the coding sprint, there can be some progress on this front. I'm also really excited to get a little bit, at least back into the discussion. I've been a little absent from it, but it's cool to see that it's moving forward. Yeah, and with this, I would like to end. I hope that maybe this gave some new thoughts or perspectives or impulses from listening to kind of my own personal experiences with adding features to Nilearn. And I want to thank everyone that has made it possible for me to have those experiences and share them with you today. So yeah, so I'm looking forward to questions or thoughts or discussion.
Thank you very much, Ula. This was absolutely a great talk to hear. I mean, for us, you have yeah, clapping, absolutely. You have a different point of view than we do, because Nilearn was born in our team, so it's really interesting to hear what you have to say. We should be taking questions, and I'll use my privilege to ask a first one. If you look back, I'm pretty sure it wasn't easy. And is there any, anything that strikes as particularly difficult?
I mean, I think the most difficult is really the first step of kind of getting into it and finding the right project, so to say, like finding a problem that you are excited about, that you are able to do, and that also people are excited about too and are going to help you or are going to support you on. Because I think from there, it was really... there's really a lot of support in the community once you start doing something, I would say. And yeah, and I think as long as you're like open to that, those were not for me the big issues. For me, I think it was really once I knew, okay, I'm going to work on this, and people apparently think it's a good idea for me to work on this. Yeah, I think that's maybe the biggest hurdle. And then, I mean, in terms of surfaces, the biggest problem, as I mentioned, it's that people should finally decide on one file format. But yeah, in terms of the process itself, I think that's it.
Yeah, that's a very interesting comment. There's a bunch of problems that are best solved outside of Nilearn. And yeah, figuring out the right surface representation is probably one. Roberto has a question. He's asking whether the scope of the surface aspect of Nilearn is exclusive to function and functional data. I think you can answer this one.
Wait, can you repeat that? Or
his question is whether the scope of the surface part of Nilearn is exclusively limited to a function.
Yeah. No, I wouldn't say. I think in terms of visualization and loading, etc., it's even typically it would be easier to have anatomical data, unless I'm not sure if, because it's coming from Roberto, if he has something very specific in mind, that then again might be maybe too specialized to fit the scope. But there's a bunch of tools for maturing folding, for example. Yeah, I mean, I think this would be one of the questions for like, is this in the scope of Nilearn?
Absolutely, and there, I think the scope of Nilearn is defined as tools for statistical analysis, and you do statistics on anatomy too. So we wouldn't see extraction of structure as part of Nilearn, but any statistical pipeline that works in surface, I think, would be part of Nilearn. Now that gets complicated because if you do part of the surface pipeline is going to be extracting the cortical thickness. That would not be part of Nilearn. But doing analysis on cortical thickness maps would be.
And I think...
So Susa...
Yeah,
I think
go ahead. The advantage of that would also be, one problem I haven't spoken about is that for visualizing surfaces, what is really, really helpful is to have the curvature and the depth of like of Salzai, and so just to have the right shading basically. And we use that from FreeSurfer right now, but if I understand Roberto correctly, then if you're measuring folding, you would potentially be able to construct these kind of maps yourself and wouldn't be dependent on having those maps available from FreeSurfer, for example. If you, for example, made your surface with a different software.
So Nilearn uses brain sprites for, Roberto asks, Nilearn uses brain sprites for visualizing volumetric images, and he asks whether we would be open to other JavaScript visualization. Or there is, you can visualize 3D surfaces that's built using Plotly. And I think it all goes back to trade-offs that Julia mentioned. So we can only depend on either fairly mature libraries or libraries that we feel that we can fix ourselves. BrainSprite was more the library that we feel that we can fix ourselves. So it's, as Julia mentioned, it's a question of how much do we put on? Julia, do you have an opinion on that?
Yeah, no, I think that makes sense. I think there was something else. Hmm?
Well, there was a question about tutorial for writing tests for Nilearn code, and there will be one in the later today.
Mm-hmm. And there's a question about the texture term, same as metric for values. But there are some answers to that. Yeah, I think this just like reflects again the mess of services of like, because even as I was preparing this, I was like, now actually in some of the new functions, I think we use texture. I've always used data, but data is of course very unspecific. So yeah, even that, like you can talk about meshes and surfaces and geometry. You can talk about textures and data, and like it's
Well, I think that really shows the effort that we're trying to do in Nilearn. You know, it's you come to something that's very much a jargon. I remember the first time I ever tried to open a neuroimaging file. It was many years ago. NiPi was still its infancy, and I wasn't doing neuroimaging. And somebody gave me an analyze file, so you know, image and header, and I was like, "What's this? I have no idea." So I tried to open the header using some random program. I tried to open the image using another random program. I had absolutely no idea. So it's really this impedance matching. And we would like to think that there's none of this impedance matching because we're all in a community. But that's not actually really true because there are many sub-communities. And ideally, Nilearn doesn't want to have a monoculture. We don't want to be something that, stick to a too strong point of view. And that's hard.
Yeah, and I think there was a comment also on that question that I think with surfaces, in addition, some of the terminology and even some of the formats and some of the software comes from not from neuroimaging, right? Like comes from 3D mesh, like I don't know, like gaming or something. Like I've used some software that people use to make computer games to work with some of the meshes. So I think that brings in an additional variable into the mix that makes it sometimes trickier, sometimes also it's cool because you can use a lot of the tools that maybe other communities have thought about before and adapt them.
So can you comment, we're going to be running out of time, it's going to be time for a break, but can you comment on the amount of effort Because, I mean, you added you contributed the nuclei of a fairly major aspect of Nilearn, a fairly major new aspect of Nilearn. I really I thought it was very interesting to hear you reflect on the choices we made back then on what to start with, and yeah, with Insight. I think they were the right choices, but it's always challenging to know. But can you comment on the time it took, the effort it took compared to your expectations?
I think so where it is a little bit misleading is I think because I was working on somehow different projects in parallel, trying to come up with functions for example, the loading, etc., into Python, because I just also needed it for my own stuff. And I had some parallel projects where I could reuse some code. I think where I was really surprised, and that's why I put it a little bit in the presentation as well, is that, once I had my code up and running, I was like, great, this works. And then comes all of the work of testing and making an example, and even hosting this data set on Nitric. And so I think that was what I didn't expect, because I didn't have any experience in really adding substantial features to a software. But where I also learned most, I think in terms of the functions themselves, that was more what I had expected, because I had kind of worked with this before myself.
So basically the fact that between works on my computer to works on everybody's computer, there's a times 10 effort.
Yes.
So that's the difference between a pile of code and software.
Exactly. But yeah, I think that was really what I took out of this the most, and where I really appreciated the input I got and the help I got, where I feel, at least for me, there is this hesitation of entering something like this where I'm like, I have no idea how these things work, and that there can be a culture that is a bit broy, or a bit like, well, you did this wrong, or you used the wrong term or something. And that I have really not found in this project or in this community, which I think is really helpful. So that, when you miss something, or when you haven't done tests and you don't even know what that really means, then someone just goes and explains it to you instead of kind of laughing about it. So yeah, I think that is a big plus for learning these kind of things in this community, this project, for sure.
But on the other hand, you stuck around. I mean, my impression is that it was a big effort on your side, that it took a lot of work from you, and I'm extremely grateful. And I think, I think it was really great to have you or others sticking around. This is what makes the community greater. We do try. Everybody tries to be friendly and helpful. Sometimes people are tired. And I mean, I don't think it has happened too much, but you're exhausted, and then you don't answer questions, for instance, which is unfortunate.
Yeah, for sure. But I think, just as a last comment, I think that's also a big point of sticking around. It is just really coming. I was really tempted to come to the coding sprint in Montreal, although, I mean, now it's not. Now it's virtual. Although this really didn't fit at all with my plans, because it's just really fun. I always learn something new. And maybe a last kind of advice, also to have this inside your academic career. For me, I did this little, this project reports that are supported by BrainHack. I, in the end, actually did a little technical report, and I used all of this for my PhD thesis. Not all of the people in my committee really got it or really appreciated it, but I think in the end, it can also be a way of, doing this kind of work that is really helpful for you and for the community, and then still getting some measure of, the classic academic accountability out of it. At least that's how I've tried to do it. It's not at least get tons of citations or something, but at least you can point to it and be like, I actually did this. Yeah.
Right. I hear two very important things that you've said that go in the same direction, is that when you were working this code, it was synergetic with some of the problems that you had. And I think that's crucial. And then, later on, you feel it has brought something to you. And I think that's something crucial for open source, is open source should also bring something to you. If it doesn't, then you're barking at the wrong tree. I think that's really important because it's a lot of work, so you're going to get tired. My feeling about open source in academia, and I'm a bit special because that was a very important part of my career, is that the skills that I've learned doing open source were just crucial in every single aspect of my career. It's useful to know how to code. It's useful to know how to work with projects and big teams. It's useful to know how to describe things in a simple way, which we do in a documentation. And it's undervalued in a formal academic resume. It's not boxes you tick. But I think these are factors of success to go further and achieve big things. That's my opinion.
Yeah, for sure.
All right, we're scheduled to have a break. I am going to leave this running, but and if you want to stay on screen, you're welcome to, but you can also give yourself a break. If there are any questions or anything, so we schedule rather large breaks because online events can actually be absolutely exhausting. You might have a life in the house, a dog or a kid to feed, I don't know. So we're going to keep this running, and if there wants to be any kind of chat or questions in the chat, this is all good. And we will resume. And there's the online town where we can go and chat. That's a lot of fun, by the way. I advise you to test the online town. It's a huge amount of fun. And so we'll see you all soon for Bertrand's talk. Thank you very much, Julia. This was absolutely great.
Thanks.